All right, so continuing on, the next thing we're going to look at would be estimation of differences between two treatment means. So what we want to look at now would be a difference between two treatment means. And I'm using the notation here mu sub j minus mu sub j prime, where j and j prime are different. All right, so this is the kind of thing we're wanting to estimate here. So for example, mu1 minus mu2, mu3 minus mu5, or whatever. All right, that's the kind of thing that we're wanting to estimate here. Now, an unbiased estimator of a difference between treatment means, mu sub j minus mu sub j prime, is given by the corresponding difference between the treatment sample means. All right, and so look here at the right-hand side. And this is why we had to know how to estimate the individual treatment means first. All right, because we use those in constructing these estimators of, for example, an estimate of a difference between two treatment means. And so y bar sub dot j, that is the mean of the sample of values that or the mean of the observations that receive treatment j, and then y bar sub dot j prime, that is the mean of the observations that received treatment j prime. And because each of those is an unbiased estimator for the corresponding treatment mean, that is how we come up with an unbiased estimator for the difference between the two treatment means. And so this notation here on the left-hand side, the mu sub j minus mu sub j prime with a big hat on top. Okay, that's the notation that we'll use for the estimator for the difference between those two treatment means. That is given by, or it's equal to, mu hat sub j minus mu hat sub j prime, which again is the difference between the corresponding sample means, the means of the samples receiving treatment j and treatment j prime. Now, the variance of that difference of sample means, the variance of that point estimator for the difference between the treatment means, in other words, the variance of mu sub j minus mu sub j prime with the big hat on it, it can be shown that that's equal to 2 times sigma squared over r, where again r is the number of blocks, the number of replications in this case, and sigma squared is again the variance of the error term. All right. Now, once we have this expression for the variance of our point estimator, we take its square root and we get this expression for the standard deviation of mu sub j minus mu sub j prime with a big hat. Okay, now, one of the important things to point out here, to notice, is that these expressions, the variance and the standard deviation of the estimator of mu sub j minus mu sub j prime, these expressions do not involve the block variance sigma squared sub beta. They only involve the error variance sigma squared. This is the reason why we do blocking in the first place, because when we make comparisons or test hypotheses about or make inferences about the treatment means where we're comparing the treatment means as we are via this difference, okay, when we're doing it like this, the variability due to blocks gets filtered out, all right? And because it's filtered out, that is why the variance and standard deviation for this estimated difference do not involve the block variance. It only involves the error variance. All right, and so that's because of that, we're going to get more precise estimators than would be the case if we did not block or didn't account for blocking. And we'll also have hypotheses tested are more powerful, again, because that variability that is due to blocks is being filtered out, because essentially what we're doing here is we're able to make comparisons within blocks and then pool those comparisons across blocks to get our estimators. Now, it may not be obvious that that's what's happening here, all right, but underlying all the mathematics, that's actually what's happening, all right. And when we take these differences between the two treatments, treatment J and J prime, within a block, then that block variability gets subtracted out or cancels out. So we have these expressions for the variance and the standard deviation for the estimated difference between the two treatment means. But because the error variance is unknown, and again, that's the only variance component that's that is here in these expressions for the variance and the standard deviation. But because we don't know sigma squared, we cannot calculate the actual variance and the actual standard deviation for that point estimator. And so what we have to do is we have to estimate the variance and the standard deviation. Now we can do that because we have estimators for sigma squared and sigma squared sub beta. And so estimators of the variance and the standard deviation of the estimator of the difference between treatment means are given by the following expressions. So the estimated variance of the estimated difference between mu sub j and mu sub j prime is 2 times the mean squared error divided by the number of blocks. And the estimated standard deviation for the estimated difference between mu sub j and mu sub j prime would then be the square root of that. So the square root of 2 times the MSE from the ANOVA table divided by R, the number of blocks. Now, it turns out that in this case, we are able to find the interval coefficient in order to construct confidence intervals. All right, the number of, let me just back up here a second. Because the estimated standard deviation for the estimated treatment difference only involves the mean squared error, okay, which again is the case because the variance and standard deviation of this estimated difference only involves sigma squared. Because of that, the reference distribution, or the distribution from which we get the interval coefficient, is the t-distribution with degrees of freedom equal to the degrees of freedom for the MSE, which you'll remember were equal to r minus 1 times t minus 1. And so that is the distribution from which we get the interval coefficient for our confidence intervals. And so if we wanted to construct a 1 minus alpha times 100% lower confidence limit for mu sub j minus mu sub j prime, then here is the formula for computing that. All right, and we've plugged in the values here so that we have a very explicit expression for that lower confidence limit. If what we were after was just an upper confidence limit alone for mu sub j minus mu sub j prime, then instead of subtracting, all right, the margin of error, we would add the margin of error to the point estimate. Okay, and again, in both cases here, the interval coefficient, the t-value, comes from the t-distribution with r minus 1 times t minus 1 degrees of freedom. And then if we needed a two-sided confidence interval for the difference between the treatment means, then we would use the following. Here's the formula for the two-sided confidence interval estimate of mu sub j minus mu sub j prime. All right, so we start off with our point estimator, and then we go a distance to the left and to the right. In other words, we subtract and we add a value that is equal to the margin of error for the interval, and that margin of error, as we discussed previously, is equal to the product of the interval coefficient and the estimated standard error of our point estimator. And as we stated a minute ago, the interval coefficient comes from the t-distribution with degrees of freedom equal to r minus 1 times t minus 1. And let me just point out something just so that we can be really careful. When we're constructing a two-sided confidence interval, notice that we have alpha over 2, right? So we're putting half of that alpha in the left tail, half of the alpha in the right tail, all right? And so the interval coefficient here is the upper alpha over 2 percentage point from that t-distribution with degrees of freedom equal to r minus 1 times t minus 1. If I go back a couple slides, then again, if what we want is a lower confidence limit alone, all right, then notice that we do not divide that alpha by 2, all right, and so the interval coefficient here would be the upper alpha percentage point of the t-distribution with r minus 1 times t minus 1 degrees of freedom. And then finally, if what we wanted was an upper confidence limit alone for mu sub j minus mu sub j prime, then again, we don't divide the alpha by 2. So the interval coefficient would be the upper alpha percentage point of this t-distribution with r minus 1 times t minus 1 degrees of freedom. All right, so that's the procedure for computing both a point estimate and a confidence interval estimate for a difference between two treatment means. All right, and so we'll pick up the next scenario in the next lecture video.